Great. Well, good afternoon, everyone. I'm Evan Coombs, Mahmoud Sharif. To start out, I know it says unmanned ground vehicle on the presentation stuff, but we've had a little bit of a name change to make our project a bit more relevant to what we're actually doing. We just can't really change it through the school just quite yet. But we are Unmanned Search and Rescue, USR. Our advisors for the past couple quarters and stuff are Professor Rankinsmeyer, who's our primary investigator. We also have Drs. Ken Meese and Solmaz Kita, as well as Dr. Vince Fong, Colin Sledge, and Chris Pritchett on as technical advisors for this project. So the scope of our project is to build an autonomous UAV vehicle for search and rescue. So last quarter, we'd been looking at designing a rover to then have two UAVs sort of take off and look for people who may be lost, because we found that searching from the air is the best way to sort of look for somebody who's missing. But we realized that, designing a rover, those types of things have already been done. Google has their autonomous car. So we decided to focus more on the aerial part of the project. So for this quarter, we're designing a plane. For next quarter, we're going to have a fully designed plane that's capable of vertical takeoff and landing, and also the controls program to be able to set its own flight path and follow that flight path based on a set of specific data inputted by a person. So a little bit on how we got from where we were last quarter and where we've come this quarter to where we are now. So right now we have two Raven RQ-11 planes. It's one of them, you can see it in the picture, and an octocopter that we're building. So we're using these as test vehicles to try to figure out how the plane next quarter is going to fly. So we have two small planes to look at how does our control program work, does it fly in the right flight patterns, does it fly well, and also those things were about $100, so if we crash one of those, it's a lot easier to replace if we need to than our first class plane. We're also building an octocopter to look at the flight dynamics of how do we do vertical takeoff. It should be very easy to sort of construct and deconstruct in different shapes, depending on where you want to put the motion things, to be able to mimic how a plane would be able to take off, since planes don't usually have rotors mounted in such an equal pattern. So our design goals for this quarter, or for the end of the project, is to build a full-size UAV to be able to fly in at least a 5-mile radius. They were shooting for more of a 1-hour flight time. It has to have 2 solar panels on top for recharging capabilities. It also needs to be able to carry thermal and video cameras, because as we said, we're doing search and rescue, so we need to have some way to find the people we're looking for. And it needs to be able to fly reliably in almost any weather conditions. So it needs to be waterproof, heat-proof, and be able to fly at all kinds of different altitudes. So you might ask, why are we using solar? Well, partially because we have 2 solar panels, and also for a lot of reasons for autonomy. So planes nowadays either have to do refueling, or if you have an electric car, you have to go and let it charge for a long period of time. We'd like our planes to be able to stay out autonomously pretty much forever. So with these solar panels, not only do you have a slightly extended flight time, but you also get to land pretty much anywhere. You can sit for a day, sit for a couple of hours and charge, and move on to your next target. But it can also sit pretty much indefinitely. So say you have 10 or so of these around a national park, they can just sit up on the top of a hill, transmit data back and forth, and be ready to fly at a moment's notice. So as I was saying, they'll have a lot of radios and stuff. So with the solar power, you'll be able to use them also as a radio repeater. So I'm not sure if you guys are familiar with how FireChat works, but it basically utilizes different forms of communication to be able to get a signal from one point to another when there's no cell phone towers or radio. So if you have a lot of these planes with their solar power and the radios, they can send data from one to the next and reach places that you wouldn't normally be able to for other forms of communication. It's also, like I said, a sustainable form of autonomy. So it's completely clean energy. We're just getting power from the sun, which is basically limitless at this point.
All right, so for our software, we pretty much divided the controls code into 3 different parts. And for the first one, we had to establish a radius of search. So how does the plane, when it gets the command to start searching, how does it determine the area of search? And we came down to the list of reasons of how you're going to get that area of search First one is your last known coordinates. So depending on where that person was last seen, we can start with there. And their age and physical attributes. From there, we can figure out how far they can go within that area from their last seen location. Their fitness and capability, how far they can go means their mile times, average time for that age period, weather and terrain, if you have mountains, if you have hills, if you have valleys, all of these somehow have an effect on your radius of search, and your time since last seen, obviously, how much time has elapsed since you've lost contact with that person. Then, when you figure out the area of search, you have to plot your flight path points. And basic search patterns that have been determined from the Army, the Coast Guards, all of these people, they figure out that there's 3 optimum ways for searching an area, and depending on what you have and the situation that you're at, you can choose a specific pattern. For the first one, the parallel search pattern is when you have no idea where that person is in your given area. There's an equal probability that they could be anywhere in that area. So you just have to cover the entire area. It's obviously the slowest and like the least creative of them all. Then you have the sector pattern where if you have a specific probability of where that person might be, so for example, if in that given area of search there's a mountain, so obviously that person won't be in that mountain, so you have to cover places that aren't that high up in altitude, or places that are close to water. So you start figuring out the probability of where that person might be. And then the last one, the trackline search pattern, is if you have an idea where he's going to be. So if, let's say, for example, that person had a mission to go to a specific point, whether that person was supposed to be going, say the person got lost crashed their plane and they're supposed to be going to a specific meeting point, then you figure out that pretty much they're going to go from A to B, and you're going to cover an area around that path from A to B. Then for the last part of our program, we have to use our thermal sensors. So when that plane is searching in that given area of search, using whatever pattern they're using, the thermal sensors, thermal cameras have to be on, and what they do is that they're trying to take images to detect human shapes. So obviously they'll be able to determine large animals, but mainly what it tries to do is that to figure out if that shape if that detected temperature is human or not, by shape, number one. Number two, by using body heat signatures. So we know the temperature of a human being is between, let's say, 35 to 40 degrees Celsius. So you know that those are the temperatures that you want to pick up. Anything less, anything more is probably not human. And then what it does is that it transmits those coordinates when a shape is recognized. So it figures out, okay, so that the plane found three thermal signatures at a given human temperatures, and those are the ones that they have to look at.
Alright, so to accomplish our goal to make the VTOL, we split our team into 3 smaller teams, where Alpha team was in charge of building the octocopter. And as you can see in the picture, our octocopter is not a traditional design, it's square, because that is the final design for our fuselage that we're building for the main plane that we are looking to build. So the idea is that we can generally arrange the wings at any geometry that we prefer, so we can analyze which geometry would give us the most thrust, or which gives us the most efficiency, and the build of that is quite constructible in any way we want to, and it has to house a solar panel, and that's kind of our big goal to push for. And then the timeline for Alpha Team was to design the octocopter, and we will be testing it by week 8. We have all the materials ready, and we're in the process of building it, and then we'll be testing it in time. And for the VTOL plane, we're gathering data from what we find from the octocopter, and then putting it into the VTOL aspect, and they're in charge of building the fuselage for the main plane. So we have done SolidWorks design on it, and it's based on truss systems. So it is quite structural, and it's made of balsa wood. So we had to be very smart on how we would build the design to be more stable. And then beta and gamma teams are the ones that were working with the RQ-11s. Their objective was to work with the flight plan, the software. So we built the RQ-11s and looked at what was the process that took to build them. And then that was the process that we will be using to find the components for the VTOL plane. So extending on that, the aspect that Evan's talked about, that if we were to crack, the software wasn't up to date and we were to test it, it would be much easier to test on a $100 plane and crash it than having the prototype, which is full scale, to crash it, and that would set us back a long time. So the beta and gamma team deadlines are on point. We built the planes already, and we're waiting for the software, and then we're gonna fly the planes. And the team's contribution for the VTOL plane is that they will be making the nose cone of the final plane and the tail section. They've done the SolidWorks on it to see if it'll pass the stresses that we'll be putting on it. And we will be building them within week 8.
So Mahmood's already talked about controls, but we also have the final team, which is our electrical team. So far they've done all the power calculations necessary for the 2 RQ-11s as well as the octocopter, deciding things on which batteries are necessary, what are the power requirements for the full-size plane as well. But they're also looking at developing how do we match the solar chargers and the solar energy to our battery packs, how do we make sure we have enough power going in, what is our flight time, how long is it going to take to recharge the full plane. And so this coming few weeks and in the next quarter, they're actually going to be designing and building custom higher performance battery packs. So looking at different technologies, such as the Panasonic, I think, AA's, which are well expensive, very, very high performance, and possibly making their own battery pack cells out of those. So trying to get away from sort of like RC hobby things that are already built and really producing stuff for R&D. So they've already designed and assembled the entire solar charging system, so that's able to be connected to the plane whenever that's finished building. As I said, moving away from the premium batteries. So we are currently working on the building of the VTOL. So how are we going to get it off the ground? All of our parts have been modeled. A lot of them are actually built right now. As you can see, that's one of our wings with a couple of carbon fiber spars in the middle and some nice balsa airfoils that we designed and had laser cut just last week. So yeah, all of the electrical systems are ready to be inputted. The fuselage fabrication is in progress. We're actually currently building that right now. And I know the beta and gamma teams are working on the nose cone, I think, as we speak. And then for next quarter, we're going to be upgrading some of the electronics on the plane as well. So right now we have an APM autopilot module, which is good enough to fly most things, but we're looking to upgrade a little bit, and we'll be running the Pixlock autopilot, which is a lot more powerful. It's going to be able to do things and say, oh, this is a tree, let me just fly around it instead of climbing 100 feet to go over some obstacles and whatnot. We'll also be incorporating a satellite data connection, the GSP 720, to be able to get in contact with any of the planes that might be out past radio range and different things. I think we're also looking into the radio transmitters, as I said, to work how FireChat does and be able to connect one to the next to the next. And also so we can talk locally to different people. So for our spring timeline, we're going to be working on a second iteration of the plane. So right now, most things are made out of balsa wood with a little bit of carbon fiber, but we're going to try to optimize more for weight and increase efficiency. So we're sort of pulling different parts off of our different planes. We've got motors coming off the octocopter power right now. So really trying to make a fully fledged model in the spring quarter. We're also going to be looking into doing our own carbon fiber manufacturing through resin infusion to be able to build much stronger and lighter fuselages that can withstand quite a bit more than what we're building right now. We'll also be doing a lot of flight performance testing. So we want it to be able to stay up for at least an hour, but if we can tweak the wings or tweak the aerodynamics and such for a longer flight time or better handling capabilities. We're going to try to work on that as well. And then we'll be doing full live person testing sometime in spring. So we'll probably have a couple people maybe be out in the desert somewhere and input to the program where we think they are and their characteristics, and actually let the plane fly and see if we can